Yes, I can hear you, I can see you, and I can see the screen also. Go on.
Okay, thank you. So hi, I'm Tejeshwar. I'll be presenting Twig, which is profile guided BTB prefetching for data center applications. So first little bit background, we have seen this diagram. This is a generic out of order processor and these are the front end units. So this paper will be focusing on the front end. So first, this paper analyzes 9 data center applications and they analyze the front end stalls due to the front end. And as we can see, for most of the applications, the stalls are about 40%. So so here in this application, we get around 24% of the front end stalls. And for this, we get maximum around 78% of the stalls. So for these 9 applications, we are getting around 24% to 78% front end stalls. So we also saw the decoupled front end in our lectures. So I'll just briefly go over what is decoupled front end. So decoupled front end introduces decoupled front end with FDIP. FDIP stands for Fetch Directed Instruction Prefetching. So this basically introduces a new queue, which is fetch target queue between branch predictor and instruction prefetch. So FTQ has the instruction iCache lines, which will be used in future. So those can be used for prefetching the iCache lines. And this queue allows branch predictor and instruction prefetch unit to work independently. So next, this Twig analyzes the limitations of FDIP. So to analyze the limitations of FDIP, they have conducted 2 experiments in which they first make iCache ideal. That means we will get 100% hit rates in iCache, and they analyze the performance with the performance speedup, and then they make BTB ideal, and then they analyze the performance benefits. So on average, they are seeing 24% performance benefits with respect to the baseline FDIP with ideal iCache and 31% with ideal BTB. Since we are getting more performance benefits with ideal BTB, they are focusing on improving BTB performance. So before we go into Twig, let's take a look at a couple of prior works done in BTB prefetching. One of the prior work is Confluence. So Confluence works on the very simple observation that the same metadata will be required for prefetching iCache and BTB prefetching. So because of that, they changed the BTB organization to match the iCache granularity, which is iCache line. Normally, BTBs are organized based on branch addresses. And the limitation of this particular Confluence is they are using record and replay for both iCache and BTB prefetching. This limits the coverage of BTB misses. We will see how that in a couple of slides. The next prior work is Shotgun. This works on the observation that unconditional branches contribute to only 21% of the dynamic branches, which is a small fraction compared to the total number of dynamic branches, and it contributes to about 37% of BTB misses. So Shotgun is statically partitioning the conditional and unconditional branch entries in BTB. And then Shotgun is also recording the iCache footprints and basically replaying them. So whenever the same unconditional branch is encountered next time, they will prefetch the corresponding recorded footprint and pre-decode the corresponding conditional branches to prefetch the BTB entries. So the limitations of Shotgun are basically, since they are doing static partitioning, so the static partition will be too small for some of the applications or too large for some of the other applications. So either they are wasting very useful BTB entries if the partition is too large for the applications, or they are thrashing each other. And again, Shotgun is also using record and replay. Now to see how record and replay is one of the limiting factors for BTB miss coverage, what we will do is we will classify BTB misses into 3 categories. One is new, means basically if we get a BTB miss for the first time. Next is recurring, which is as the name suggests, the repetitive BTB misses, and non-repetitive or non-repetitive BTB misses. Now, if we look at the division of BTB misses with respect to these three categories we just saw for all of these 9 data center applications, as here you can see for all of the applications, the majority of the BTB misses are recurring BTB misses. On average, there are like 52% of the BTB misses are recurring misses, but still there are 48% of BTB misses which are either non-repetitive or new, and both of them are not covered by Confluence and Shotgun, because Confluence and Shotgun, both of them work on record and replay. So on average, 48% will not be covered by Confluence and Shotgun. Now we also take a look at what are the challenges with hardware BTB prefetchers. Both Confluence and Shotgun are hardware BTB prefetchers. First of all, for to prefetch, we also need to decode the branches to get the target address. So it will create hardware overhead of adding additional decoders. And the latency will also depend on whether that particular branch instruction is there in iCache or not. If it is not there in iCache, then the prefetch latency will be deteriorated. Now, how Twig, we will see how Twig addresses these two challenges. And so Twig basically uses the software BTB prefetching to prefetch the to timely prefetch costly BTB misses by inserting new instructions during compilation. And BTB Prefetch Coalescing is another contribution where they are coalescing, combining multiple BTB prefetch operations to reduce static and dynamic instruction overheads. Now I'll give you briefly how Twig works in a nutshell. So let's consider we have a dynamic profile, dynamic execution profile of any application leading up to any particular a particular BTB miss. And let's say these are A, B, C. These are the basic blocks leading up to a BTB miss at this particular in this particular basic block, and we are calling it critical BTB miss to the branch pieces with large number of BTB misses. Now what we want is to avoid BTB miss at this point. We want to prefetch this particular BTB entry somewhere in the preceding basic blocks. So somewhere before this particular critical miss, we want to initiate the prefetch. So this is what Twig is doing. So now we have to address following points. First, we need to identify the branch pieces which are generating these large number of BTB misses. Then we need to figure out a way to initiate this prefetch request for such BTB misses. And we also need to find out when to initiate actually these BTB misses so that for the timely prefetch. Now let's see how how Twig addresses these issues. So first, for Twig software BTB prefetching, first Twig analyzes the binaries of application to identify the PCs and target of every direct branch. Then Twig is using the dynamic execution profile to find the PCs with large number of BTB misses. And lastly, it will modify the binary to add new instruction to prefetch corresponding BTB entry in timely manner. So this answers our first how to identify the branches. So using the dynamic execution profile, it will identify the branches which are generating large number of BTB misses. Now to prefetch a particular BTB entry, they have introduced a new instruction, BR-prefetch. So BR-prefetch has two operands, which is basically branch instruction address and corresponding target address. These are instruction pointers. And the operation, the functionality of BR-prefetch is it will add a corresponding entry in BTB entry with this branch address and branch target address. So this is how Twig handles the second problem, which is how to initiate the prefetch request. Now we have to figure out where to insert this particular BR prefetch for timely prefetching of particular BTB entry. So for that, let's consider that we have at particular address A, we have six unique BTB misses, and we to prefetch timely, let's leave some prefetch distance, let's say for like 20 cycles, and before this 20 cycles we have some preceding basic blocks which are leading up to these BTB misses. Now if we focus on these two particular misses, miss number 2 and 3, we can see that here both of these paths have basic block E. That means if we include our branch prefetch instruction, if we insert it in the basic block E, it will be effective to cover these two misses. So that's how we can calculate that for basic block E, there are it can cover two unique misses at basic block A. Similarly, we can do these calculations for other blocks also, C, B, and D, and basically we can calculate, we can fill this table. So for B we will get 4, for C also it is covering 4, and D and E is covering only 2 unique misses. Now since we have the execution profile also, that means we know each and how many times each particular basic block is being executed. So we have that total number of executed per basic block also. Using these two, we can calculate the probability of success. So we can calculate the probability of BTB miss at A given any particular basic block. So these are the probabilities calculated for all of the potential basic blocks. Now let's go back to our trace. Now here, let's focus on these four BTB misses at A. So for all these 4 BTB misses, we can insert our prefetch instruction in either B or C, or basic block B or C. So these are our possible locations, and from the previous table we have the probabilities for B and C, and B has 25% and C has 50%. So we will choose to insert our instruction in basic block C. Similarly, for these two BTB misses, we have potential candidates of to insert basic blocks D and E with their corresponding probabilities of 33% and 66%. In this case, we will insert our instruction at location E, in basic block E. Now, this is how we address the third point, when to initiate. We initiate it in the preceding basic blocks with higher probability of success. Now, since we have created new instructions, we are adding new instructions, so it is going to create some storage cost. So it will create some significant storage cost because we are storing instruction pointers for both branch address and its target, and they can be as large as 48-bit signed integers. So we need to see how we can reduce them. So to reduce them, instead of storing absolute values of these addresses, we can store the offsets. We can store the offset between the prefetch instruction and corresponding branch instruction. And we can also store the offset between branch and its corresponding target instruction. Now we'll see how effective these offsets are. So to see that, we will take a look at the CDF of prefetch instruction to branch offset. And here, if you look at here, we need only 12 bits to store 80% of all of the branch offsets. Similarly, for branch to target offsets, if we take a look at here also we need 12 bits to store 80% of all of the branch targets for most of the applications, except for this one application which has little bit more branches with higher offset. So now we are storing, instead of storing absolute address, we are storing the offsets. So there could be some of the branches which are too large to encode. Encode. The offset could be too large to encode using just 12 bits. So in that case, what they are proposing is they are proposing to store them as a key value pair in the memory, and then they are storing all such addresses in a sorted order of branches. And they are prefetching such multiple key value pairs so that they can use just one operation to prefetch multiple entries. And since they are stored in sorted order, they are hoping to utilize the locality. So to do this, they have introduced a new instruction, which is branch coalesce. Branch coalesce is taking two values as input. One is the address for a key value pair, and second is 8-bit bitmask, which will indicate how many multiple consecutive entries we are prefetching. And the functionality is to prefetch the multiple consecutive entries. Now we will look into the results, simulator results. They are using cycle accurate simulator, and they are using 8K entry 4-way BTB, and these are the other configurations. So this is the speed up over the baseline FDIP, which is decoupled front end. Now, if you focus on any of the applications, for example, this application, so here you can see that okay, so before I go there, the first blue bar is Confluence, the second one is Shotgun. These are the two of the hardware-based state-of-the-art prefetchers. Then this bar represents Twig, and this particular purple bar represents 32K entry BTB. So our baseline is 8K entry BTB. So this purple is 32K entry BTB, and this is with ideal BTB. So here, as you can see, Twig is outperforming the state-of-the-art prefetchers, Confluence and Shotgun. The similar trend can be observed for other applications also. For some of the applications, BTB Twig, which is 8K entry with prefetching software prefetching, is even uh, outperforming the design with design with 32K entry BTB. On average, Twig is achieving 20.86 speed up compared to 31% speed up in case of ideal BTB and only 1% speed up with shotgun. Now we take a look at the BTB miss coverage. Again, here also we can see that Twig is outperforming most in all of the applications. Twig is outperforming Shotgun and Confluence, and Twig is covering on average 65% of all BTB misses. Now we'll take a look at the contribution of BTB software prefetching and coalescing. As you can see here, for most of the applications, the major contribution comes from the software BTB prefetching, because we saw that for most of the branches, only 12 bits are enough to store their offsets. So here, out of all the out of overall gain, 71% of the gain is because of BTB prefetching. Now here again, for accuracy, in prefetch accuracy also, Twig is outperforming Shotgun and Confluence in all of the applications, and on average Twig is getting 31.3% prefetch accuracy. Now, since Twig is profile-based prefetcher, so we have to also see what happens if we are profiling it on some different set of inputs and and then using that particular profile on some different inputs. So that's what here this particular graph shows. So this index 1, 2, 3 are different sets of inputs, and Twig is profiled on the set of inputs index 0. So this purple is also this purple last bar is showing the Twig performance with same input profile to compare. So if we can see for all three of the applications, the Twig with different profile and Twig with same input profile have comparable performance, and both of them are outperforming Confluence and Shotgun. Now since we are adding new instruction, we also need to take a look at what is the overhead of these instructions. So for on average, the static overhead is 6%, and dynamic overhead is much less, and on average 3% dynamic instruction overhead is there. Now they have done the sensitivity analysis with respect to the prefetch distance. We saw that I said that we are leaving 20 cycles for prefetch distance before a particular BTB miss. So they have done the sensitivity analysis with different prefetch distances. So between 15 to 25 cycles, they are getting most of the benefits. They have also done the sensitivity analysis with respect to the how many bits to use for coalesce instruction bitmask. And here also, as you can see, with 8 bits for bitmask, majority of gains are achieved. Now let's take a look at the limitations of this particular proposal. Since this is a profile guided proposal or profile guided prefetching, there is a necessity to profile every new application which we want to run with this particular architecture, and it only covers direct branches. And this is modifying ISA. That means we need to do compiler modifications, and we also need to recompile. Recompilation of existing binaries is also needed. And we also observed one key issue with their evaluation methodology. So in the evaluation methodology, when they are comparing the IPC benefits, they are not segregating the benefits due to the new instructions added and the actual benefits of the software prefetching. Because the new instruction which they have added, which is BR prefetch or branch prefetch, that is highly independent instruction. So it will highly affect the IPC. So we need to segregate the effects of that particular instruction and the actual benefits we are getting from the software prefetching. And in summary, on average, it is giving 21% speed up compared to 31% of ideal BTB. So it is coming very close to the ideal BTB performance. It covers 65% of the all BTB misses in baseline FDIP. And it incurs 6% and 3% static and dynamic instruction overheads. In conclusion, we saw that BTB misses are costlier. We saw that using the ideal BTB, and ideal iCache comparisons, and larger branch footprints in data center applications are exposing the BTB capacity limitations. And reducing BTB misses for direct branches also are benefiting for performance greatly. This is the reference, and thank you. Any questions?
Yeah, it was a good presentation overall. Just
Okay, thank you.
a question out of curiosity.
Yeah.
If you want to implement the entire approach in hardware, is it possible?
It is, let me think, it is.
Vishwa, are you trying to say the learning also online, dynamically learning and prefetching?
Yeah, you have to do it dynamic, right? If you have to do it in hardware.
Yeah.
Their main idea is okay, so one of the point they raised was that if we do anything in hardware, then to get the address, we actually need to decode the instruction.
It's okay, I can
So
give you a decoder.
yeah, we need to have additional decoder. That's one of the points. And yes, we need to figure out how to profile dynamically and find out these.
Now the definition of profiling is different, right? We are not doing profiling at a software level.
Yes, absolutely.
Yeah.
So at the end of the day, what are you getting from this profiling?
From this profiling, we are getting two things. One is what are the critical BTB misses, where we are seeing large number of BTB misses. That can be done in hardware. Second thing is we are finding out the preceding blocks where we are seeing this particular
exact timing of when
to prefetch. So
even that you can learn. This is just
this is doable. Not sir, we are not challenging the claim. It's doable, totally hardware. But then we need to come up with a mechanism that can learn online.
Find the perfect place to insert the instructions or initiate the prefetch.
Yeah, in hardware it will be initiating prefetch, not.
Yeah. It will just initiate the request. Yeah. No need of new instruction.
Since anyway you have taken this topic for your project, so
yes.
I was thinking you may just go for the initial insights of this paper and try to do it in hardware, right?
Reasons to have chosen this paper was exactly
that
this.
That I know. You guys are pretty good at all this jugaad.
Vishwa, I also wanted to personally ask you one question. We have a doubt that why do these papers who add independent instructions show IPC benefits rather than execution time benefits?
Okay, it's getting recorded. the talk is getting recorded.
Sorry. Sorry, but I found it as one of the major weaknesses because the reason is execution time benefits exactly shows us how much he has tried to reduce the execution time. But IPC, you can still increase the number of cycles and yet gain IPC benefits.
Yeah. You know the answer, right?
No, I'm not knowing as to why they are.
Yeah, we can take it offline. Anyway, it's getting
Okay, sure.
recorded.
Yeah.
Yeah.
Because their instruction BR prefetch is basically entirely independent instruction. It doesn't have any operands.
Yeah.
All of the operands are already there. It can improve IPC by huge margin.
By the way, from the same group, there is a paper in ISCA 2022 on BTB replacement.
Okay.
That came just 6 hours before, early morning today.
Oh, okay.
Okay.
Yeah. Okay, good. Any other questions, anyone? I like the presentation. It was good. It was full of insights.
Thank you, sir.
Okay, if there is nothing, we can call it a day. Anyway, 3 presentations, right? Bit of overwhelming. Okay then, Devasis, you can stop the recording.